Okay, where did we finish yesterday? I think we just barely, on my last breaths, finished deriving the result for Simpson's rule, but we didn't really have time to use it, so that's what we're going to do this morning. We'll have a look at an example. Just like with trapezoidal, we'll see how it works with basic form and then when you go a bit longer. Okay? So this is a very typical question. You get given an area or an integral equivalent to an area. Because integrals and area are so closely related, I mean, we've already established they're not the same, but they're very, very closely related. You can therefore think about this as a method of approximating the integral without even thinking about the area, if you wanted to. Okay? So it can be quite separate, and later on, probably not today, we'll see how we go. When you're looking at volumes, it has nothing to do with area, right? But it's equivalent to the integral, so that's what I'm interested in. Right, so let's start off with part A. And if we're using Simpson's rule, it says 2 sub-intervals, okay? Now, this is probably a good time to step back again and think about language. And I'm going to think about trapezoidal rule and Simpson's rule and how they differ. Simpson's. Okay, now let's just rehearse. Don't worry about when you've got multiple forms, multiple lots of it. Let's just think about the basic form of each of these rules. Can you help me remember? What is an area approximately equal to according to trapezoidal? How do we start? H on 2. Good. And then this is just one trapezium, right? So what am I going to have in there? Just one trapezium. This is, hold on, so this is a trapezium, right? So it's the perpendicular height, and then it's got 2 parallel sides, right? And I take the average of those. I've already taken the average, that's what the half is about. And the 2 parallel sides are the function values that you get, yeah? Okay, good. Now, what did we learn yesterday? The basic form of Simpson's rule, okay? You again have a perpendicular height for each little section, right? But it's h on 3. H on 3, okay? And what do we have in the brackets here? We're using a parabola to approximate the curve, okay? And a parabola needs how many points to be defined uniquely? 3 points, right? 1, 2, 3. So you've got the first and the last, just like before, right? And then you've got the midpoint. How many of the midpoint do we have? 4, right. So 4 times, I really should have given myself more space, but f of a plus b on 2, okay? Now, you can see they're quite similar, and when you start to have extra ones, right? This becomes 1, 2, 2, 2, 2, 2, 1 in the middle, right? This becomes 1, 4, 2, 4, 2, 4, 2, 4, 1, and they alternate in the middle, okay? You've also got the difference between the 2 and the 3. How do you remember that? I don't know. I know some people have been taught that for Simpson's rule, you remember that Homer Simpson has 3 children. If your mind is so inclined, that's fine, okay? A more mathematical sort of way of remembering is, look, I've got 2 values here, 1, 2, because that's what a trapezium has, so it's a 2. And I've got 1, 2, 3 values here, so that's a 3. Whatever works for you, okay? Now, let's think about these things, subintervals, function values, and so on, okay? If you have n subintervals for trapezia, right? How many function values are you going to have? Just n plus 1, right? Function values, okay? Because one trapezium, it's got 2 sides. 2 trapeziums, you've got 1, 2, 3, and so on, okay? Now how many, here's a tricky word. You'll see it, I'm going to mention it, not because I like it, not because you'll see it in exams, but because you see it in textbooks. How many times are we using the rule? Well, every time you add a new subinterval or a new trapezium, right, they call it an application of the trapezoidal rule, okay? Now you'll see in a second why this is such a confusing word and why we try and avoid it, but you'll see it sometimes. Fitz, for example, is a really bad culprit. He uses like every different kind of word possible. I think he's just trying to, tell you that there's lots of different options, but it can be very confusing at the end. So if you ever see the word, use 4 applications of trapezoidal rule, okay? What you're going to get is 4 trapezia, 4 subintervals, and 5 function values. Does that make sense? Okay, now let's compare that to Simpson's rule with parabolas and stuff, right? If I have n subintervals, Okay, so that's what I've got here. Okay, 2 subintervals. How many function values will I have? Think carefully. Think carefully. What is a subinterval? For Simpson's rule, what does it look like? It's still going to be, so this is a subinterval, right? There's one, and there's another one. So that's 2 subintervals, and that requires 1, 2, 3 function values, right? So this is still the same, n plus 1 function values, okay? But the important thing to notice here is that as opposed to trapezoidal rule, I mentioned this at the end of yesterday, right? You can pick however many subintervals you like, right? You can't just pick any number of subintervals, okay, for Simpson's rule. You can't just pick any number of function values. You need to have an odd number of function values to make Simpson's rule work, which kind of implies you need to have an even number of subintervals to make that work, okay? So, now, applications, right? That's how many trapezia you have. Here, applications would be how many parabolas you have, right? Now, if I have, let's just take this example, right? This is 2 subintervals, 3 function values. How many parabolas are there? How many applications? How many times am I using the rule? Once. 2 subintervals, 3 function values, 1 application, 1 parabola, okay? What if I wanted more accuracy? What would be the next step up, right? I'm going to have 2, right? So 2 applications. Well, what's that going to mean for the rest? Let's go 2. So, okay. So now how many subintervals? 4. How many function values? 5. So what's the relationship? It's n on 2, isn't it? N on 2 applications. Or n on 2 parabolas. Which, by the way, this tells you why this has to be even. Of course it has to be even, because if you're dividing by 2, how are you going to get an actual proper number of parabolas at the end unless this is 2, 4, 6, 8, etc. Okay? Right, now that we have that in our heads, let's actually start to answer this question. 2 subintervals, so this is the basic form, the form that I just wrote down there, okay? So I always start every single time just by writing out the formula, okay? It won't get you any marks, but it'll tell you all the things that you need to know in order to answer the question. Okay, so you start off and there's an h there, right? So what's h equal to in this case? And this is where the drawing does help you, okay? H is equal to the height of each subinterval. Now, because it's a nice easy value, you don't really need to do much sophisticated working out. You can just tell me that the perpendicular height is... The perpendicular height of each subinterval, that's what h is a half, right?
Oh, a half.
That's a half there, right? And that's a half there. It's the height of each one, okay? So h equals 1, 2. Okay. All right, now, what are all these values here, okay? A plus b on 2, and b, right? A is 1, and b is 2, so therefore the average between them is just 1.5. Okay? So now let me translate all of that. The area, therefore, or the integral rather, is approximately equal to this on 3 is a 1/6, okay? And then what have I got here? I've got f of 1, 4 lots of f of 1.5, and f of 2. Okay? So do you see what I did there? I start with the formula, and then I think, okay, what do I need to fill this out? I've worked out what those all are separately, and now I launch into here. Okay, now, a lot of people, including you guys, once you get comfortable with this, will stop doing all of these steps up here, okay? And you'll just go directly to this step. That'll be the first line you write. I have no problems with that, okay? But I'm a maths teacher, and I still write this first. Why? Number one, so I know a formula, okay? So, now that I have it in its sort of clean form, which I've memorized, okay, I won't mix up these two, okay? But secondly, it's just less error prone, right? If I have to memorize the formula and then put all the values in and work them out at the same time, in an exam, you're asking for it, Like, you guys know how frustrating it is to get back a paper, and you're like, I know how to do all this stuff. It's just silly errors, okay? So this is exam technique, right? You use a technique which is less error prone. You lose about 15 seconds to write all of that down. Is it worth the 15 seconds? I reckon it is, yeah. Where'd I write the formula?
I think you're just missing a
Oh, I'm missing the 4, which I put here.
Yeah.
Okay. Right, are we good to actually evaluate it now? So, now it's just sort of mechanical stuff, right? My function is 1 on x, okay? So 1 on 1 is that. 4 lots of, that's 3 on 2. So if I take the reciprocal, it's 2 on 3, and that's going to be a half. Okay, so you get your calculator out. I think from memory, that's what you end up on. Someone tell me, you verify it, because my memory might be a bit shady.